It's my pleasure to have here and introduce you to Professor Vahid Sandoghdar, the Maxwell Director for the Science of Life in Berlin, Germany. I had the opportunity and the great chance to work together with Vahid and collaborate in one of the most amazing and challenging experiments to couple a single organic molecule to an optical microcavity. I hope we will have one chance to talk about it today. And yeah, for those who doesn't know Vahid, I just wanted to briefly summarize his bio and some career achievements. He was born in Tehran, Iran, and studied physics at the University of California in Davis. Afterward, he did his PhD in physics in the university under the supervision of Edward Hines and Serge Haros. Then he moved from Boston to Paris with Serge, and afterwards he became head of nano-optics group and habilitation in the University of Constance, Germany. From 2001 and 2011, he moved to his group to ETH Zurich. Then he was awarded with an ERC advanced grant, and since then he moved to his actual location in Erlangen. He holds the Alexander Gold professorship in the FAU University in Erlangen and the directorship of the Maxwell. And recently, he's the founder of the physics group for the Max Planck for Medicine and Physics. And maybe we will introduce it. With this, this list of achievements will be endless. So let me stop here and think about it, and I will give him the stage. And we are looking forward to your talk.
Yeah, thanks very much, David. Thank you, Richard. Yeah, it's really a great pleasure to be here. I appreciate the opportunity to speak to you today. And when Diego said, we know each other now for many years, and it's been wonderful to see how the activities here are so lively. I've met many younger scientists, and it's impressive the breadth and the quality of the work that is done here. And it's also my first time that it's joining. All right, so my group really has been working on what we call nano-optics for now a little more than 25 years. And we started by being interested in kind of understanding light-matter interaction at a very small scale. This is the end of the 90s, and our kind of vehicle for doing this type of experiments was to look at single molecules that were not moving, because at the time other people were looking at atoms and atom traps, and that was kind of the way to go about this. Single quantum dots were emerging, and we chose to work with single molecules that are embedded in the matrix, and we really wanted to use these just as a, if you want, a two-level atom for understanding how light interacts with a single emitter, and later things like single photon sources became an issue. So coupling, kind of just the very, very basic questions of what's the coupling strength between an incoming photon and a quantum emitter is something that, in your quantum mechanics course, you just write down and move on. But if you go to the lab, you worry about how to do this best, especially if you're interested in using this type of coupling, for example, for making quantum operations or making quantum devices or doing anything where the efficiency becomes important. So we've spent a lot of time doing, in a way, very textbook type of experiments that are possibly completely useless. But we've been interested in just kind of doing in the lab what you would see in your thought experiment. And I'm going to give you an overview of some of these works that we've done over the years. Now, from those more quantum optically motivated works, we became interested in the question of microscopy because we wanted to know kind of where the molecule is. If you want to, for example, couple a molecule to a resonator or to any kind of a mode, position makes a difference. So we became interested in microscopy, and microscopy is a field that, at least in my generation, was considered to be massively boring. And it was dealt with in about half a page of your textbook in your optics course or physics course. And but since then, it's really experienced a very interesting type of evolution and revolution. And we were fortunate to be kind of part of this wave end of the 90s till today. So kind of trying to invent new types of microscopy, and at the end of the day, it's just a new measurement. So this has been interesting, and now we're more and more excited about applying whatever we've learned to actually solve some interesting biomedical questions, and that's kind of what motivates the establishment of this Max Planck Center for Physical Medicine, which will be inaugurated in a few months. And you get a little bit of a flavor from my point of view how we're trying to approach this. So that hopefully kind of motivates a little bit my title, which might seem a little strange. All right. Let's see. Here. Right. So I mentioned the question of efficiency, and so I want to start with that. So you have an object, and you illuminate it with light, and then if you look right through, you could be doing what you call usually an extinction measurement. An extinction in the sense that light is extinguished in the forward direction. So you want to know how much light is left, and quite simply, you can write the power that is attributed to this interaction as the incident power times some kind of a cross section divided by the area to which you confine the light. So that's a kind of a generic phenomenological kind of understanding of interaction between light and. Now, this seems to be more of an energy type of point of view where light is missing, so there's less intensity in the forward direction. But I'm sure many of you are aware that the essence of this interaction is basically interference. So you're sending light, and this light is being scattered by your object, and then the scattered light and the incident light are going to interfere with each other in the forward direction. And if you write it the way I've shown it, you come with something like a plane wave, and then you scatter into something that is kind of like a dipole wave. But these two don't match, and in some cases they interfere destructively, in some cases interfere constructively. So it could be in general kind of a complicated situation. But you would write that either way as such. That is, the intensity that you detect on the detector could be written as the sum of the electric field squared, right? So, this term here is what's usually called as the extinction term, and you probably have seen this in the context of the optical theorem, whether they're doing quantum mechanics or light optical theorem kind of appears, or even in particle physics. All right. Now we're worried about this question of efficiency. The question is, if I send one photon, what's the probability that this one photon really gets scattered by a single atom? There were some theoretical treatments that predicted that this will never become 100%. So in this work, we did a calculation that showed that if you were to mode match the incoming beam with the light that is being scattered by your object, in this case a point dipole, you can reach 100% extinction of the forward direction. So your dipole acts like a point mirror. That means that there is no light going in the forward direction afterwards, and all the light is going to reflect. So destructive interference in the forward direction, and if you want constructive in the backward direction. And this was quite motivating because it showed that this kind of light matter interaction could be intrinsically extremely strong. Usually if you're sitting and discussing, you would think, oh, a single atom, I have light, and it's not going to make a big difference. So I have so many cavities and all kinds of things. I'm going to show you that we also use cavities at some point. But fundamentally, it would be very exciting to think that you actually don't need anything. You can send a photon, and this one photon with 100% probability sees your little atom. And connected to that, you can also kind of argue that because the cross section of a point dipole is essentially lambda squared divided by 2, this actually corresponds to a very large area. And that's another way of thinking that, it's not very difficult to focus light down to something for lambda over 2. So that argument that sigma over A also tells you that you should get a pretty large effect. But that's kind of a little bit of a hand-waving argument, but this paper showed that you really can do that if you have the right wave that matches the scatter. If you were to not have that, but have a focused plane wave, then you can think of a plane wave as a superposition of all kinds of multipoles. And when you focus it, you put most of that into a dipolar mode, and therefore tightly focused being is also quite good, but it's not 100%. So that's the kind of thing that it should. So this is now more than 15 years ago, and we had a series of experiments to demonstrate that this actually works. And I'm going to talk about those more in the second half of the presentation. I want to focus a little more on biologically related experiments, and those happen at room temperature. At room temperature, the cross-section of an oscillating dipole or the two-level system is reduced by a very large factor compared to the ideal cross-section. And that factor is of the order of 10 to minus 5, 10 to minus 6. And the reason for it, in a way, is that you want to excite a dipole, but this dipole is constantly experiencing collisions with the environment, and it's being dephased. So you don't get to drive that transition coherently. And the ratio of the spontaneous emission rate to the overall width that you have is of the order of 10 to minus 5. And overall, so your cross-section actually at room temperature does go down by a lot. And this is the intuition that you have, that if I put a single atom or molecule that is sitting in a polymer matrix or in some kind of crystal, it's not going to have a large effect on a beam. But we showed that this small effect is still measurable. So measuring something of the order of 10 to minus 5, 10 to minus 6 is not, it's challenging, but it's not completely out of question in physics. So I'm not going to go through the technical details, but what you see here is really an image of a single molecule blocking light as you scan the light across it. But if you want, the depth of the shadow is of the order of 10 to minus 6, you see here, the scale here, 10 to minus 6. So it's a very small effect, but it's measurable. And that's kind of the take-home method that I want you to have, that at room temperature, if I have even a single molecule, it's going to scatter at the order of 10 to minus 6 when I focus tightly onto it. All right, so now let's go away from that single molecule to a finite-sized nanoparticle. And now I'm thinking of essentially a Rayleigh scatterer, an object that is spherical, much smaller than the wavelength of light, but much larger than a single molecule. If you were to kind of consider the scattering problem, then you would say the electric field that's scattered by this object can be written as the incident electric field times some kind of polarizability. And the polarizability is what you can know from your textbook. It's given by this expression. The most important feature of this polarizability is the proportionality to the volume of the object. That's something that maybe is not very interesting at first. You first look at this part, but this part is not very exciting because it's not never going to become 1,000 or 10. But by changing the size of the particle, we easily change V by a whole bunch. And of course, you know that as you reduce the size of the particle, so if you change the size of the particle by 10 times, its volume becomes smaller by 1,000 times. So that's a very, very sensitive kind of factor that you have in the dependence on size. Now, of course, you also know that polarizability is what goes into essentially your absorption cross-section and scattering cross-section. And you want to remember that polarizability is a complex quantity. So it has a real part and an imaginary part, which brings in some phase issues depending on the wavelength of the material, of your illumination, where your material goes to resonance or not, and all that stuff. But at the end of the day, you have a quantity that's called polarizability. And with that, you can understand all of the scattering properties, as long as you're in this radio regime. Now, experimentally, we had finally kind of completely disparate looking type of activity in our group about 20 years ago. We're trying to detect very small nanoparticles. Here the challenge was to detect very small gold nanoparticles, partly because that was the beginning of what you call today plasmonics, and detecting the smallest kind of plasmonic unit, which was something like a plasmonic nanoparticle, 5-6 nanometers, was very interesting for experiments. And these were not doable optically, so we needed to see it. So we showed in this paper that you actually can do this, and it turns out that it's a very simple way of doing it, and it's the same thing that I showed you essentially. We call this method now interferometric scattering microscopy, or in short, I-scan. Now, soon after that, we realized that there's not much that is so amazing about a gold nanoparticle. You think of gold as something that scatters very strongly. And that's kind of true, but again, remember that the volume factor is more important than material properties if you talk about scaling the amount of scattering. And it turns out that if you take something like a virus, and in this case, the virus that we were looking at back then was about half the size of your coronavirus. And that little virus already is large enough to scatter quite a bit. And what I'm going to show you now is the scattering image of a single virus that is diffusing on a lipid bilayer. So a lipid bilayer is depicted here. You have two layers of lipids that go on top of each other, but this is essentially a two-dimensional liquid, and therefore there's Brownian motion in it. And this virus is tethered to the lipids, and as the lipids jiggle around to a Brownian motion, they take the virus with them. And so that's kind of what you just saw. But the important thing was that we were getting the signature of the virus on the chromatograph by simply shining light and looking at the light that comes down. This is the arrangement that we do since then, quite often in the experiment, where you imagine that you have your microscope and you have a substrate, and on it there's a nanoparticle. In the very first experiment, there were gold nanoparticles. Here it was just the virus. Either way, when you illuminate that system with something like E incident, there is a field that is scattered by the object, but then there's also a field that is reflected by the substrate interface, because interface is never 100% index matched. And these two fields interfere in the backward direction. And this interference is now exactly the same as the forward interference that I told you. So you're going to get the same physics essentially, but the strength of the reflected field or the reference field now is a little different from before, but that's That's a technical. So the essence of this is the same thing as extinction, and we realize that we can do a lot with this. And to put it in context, you can do this type of experiment just as you would do your fluorescence experiments in all kinds of different modes, also in lots of different illumination and detection modes. So if you're doing a standard fluorescence experiment, you could do total internal reflection, you can do confocal, you can do light sheet, you can do this and that, right? And in principle, when you're looking at scattering, you can think of doing the same kind of palette of different illumination and detection schemes. The very first experiment that we did was done in this kind of a confocal mode. So we were focusing light and scanning the nanoparticles through it. And the most common way of doing it nowadays is this way, where we focus in the back focal plane of the microscope objective, so that afterwards you have almost parallel waves coming onto your sample, and then you image that on your camera, and you get a wide field image, and you can image with the camera, so you can be very fast and look at many things at the same time. It's also worth mentioning that this technique is probably just the newest version of a series of measurements that people have been doing for more than 150 years, all under the umbrella of interferometric microscopy. So if you go back to your literature, you actually see, interestingly, that already in the 19th century, people were doing interferometric microscopy. But you most probably think first of something like phase contrast microscopy, which got a Nobel Prize in the 20th century, and then there was the version differential interference contrast, and then with holography, which is also a brother of it. In all of these cases, you write an equation that looks like this. You have a reference field plus an object field, and then they interfere. And now the details are, where does the reference come from? Where do I detect? But the essence is the same. Now, the thing that we're doing different, right, and if you were to look only at the intensity that is scattered, that would be dark field microscopy, and we're looking at we're including the cross term. And so this term scales as the volume, whereas the dark field term scales as the square of the volume, because it's the intensity. And the dark field term drops much more quickly as you go to very small particles. That's why the traditional kind of way of looking at nanoparticles in a microscope, which is dark field microscopy, incidentally, dark field microscopy also got a Nobel Prize, does not work. So what we're really doing different from all these things that have been around in the literature is that we've focused on increasing the sensitivity of the measurement so that we can detect very small particles. So the equation is the same, the orders of magnitude of the signal are a little different. And of course, as you go to very small signals, you have to worry about your noise more and your background and things like that. So that's what we've been fighting with and trying to get a handle on for the past nearly 20 months. So we managed about 10 years ago to bring the sensitivity of iSCAT all the way to detecting single proteins. So proteins are very important in biology, and they're probably the smallest units that matter, right? Your biology also worries about small molecules, but in terms of the real building block, your protein would be probably the smallest, most important unit, but it's also DNA. So you would have your protein, for the physicists among you, a protein would be something that is of the order of 3 to 10 nanometers large, and it has an index of refraction that is of the order of 1.56. So it's not a very strongly scattering object. And that's why you usually wouldn't think that, oh, let's go look at the scatter on a single protein. But it turns out that we can actually do that with this very simple way that I've been telling you. So imagine that you have a surface, and the surface has been possibly functionalized. That's for those who are more into that. But let's say that you have a substrate. If you look at that substrate, you get an image that looks like this. And this is speckly. So it looks pretty horrible because of tiny fluctuations of the index of refraction or topography on your substrate would give you a speckle, as you're familiar with from laser speckles. And so the signal that of a single protein compared to the modulation of the speckle is actually quite small, by 1 to 2 orders of magnitude smaller. So it looks pretty bad until you realize that, okay, but this speckle is not going to change. So I can do a very simple background subtraction of subtracting 2 consecutive frames of my video that I take, let's say, and then I can flatten my field to a large extent. And now in between, if I have introduced proteins, then I can, by this subtraction, I actually get the footprint of individual proteins. So again, this is essentially an extinction image of single proteins, but done in a reflection mode in this case. So you can do this for proteins of different sizes, and of course, because as the size changes, the amount of scattering changes, fully changes, you expect the depth of this shadow to change, and this is exactly what you see here. So kilodalton is the measure for the mass, right? So you go from 340 kilodalton to about 60 kilodalton. You see that this is quite dark, and this is now becoming comparable to the residual modulations that we have on. And these residual modulations are things that are still remaining even after I subtract my background, because my background subtraction in experimental life never. Now, but if you do this experiment for a whole bunch of proteins, and then you can make histograms and figure out the contrast that you're detecting here, like this contrast that you're seeing, and you can identify different populations. And in particular, we could show that the signal that we're getting is pretty much linearly proportional to the mass of the proteins that we're putting. Now, this is not completely obvious because I showed you I told you about proportionality with volume, and now you can see that it's actually also proportionality with mass. And that is something that is not necessarily going to be always like that, but at the kind of the precision that we have, it turns out to be the case right now. And we have shown that we can now improve the sensitivity also by throwing in some machine learning to help us detect those small signals on top of the difficult background. So what the machine learning program algorithm does here basically tries to be smart about what is the feature of the signal and what's the feature of the background, and it can tell the small extinction signal of the protein on top of this kind of a spectrum. We can talk about it. Now, this has been now established in the field, and it's gotten the name mass photometry. And the group that has really been pushing this is the group of Philip Kubura, who used to work with us in Zurich. And now he leads a group at the University of Oxford. And they have been collaborating with protein scientists, and they have really brought this to a point that has become a quantitative measure of mass. And this is the paper that they published in 2018, where you see that the signal from different proteins now quite nicely lie in a linear ladder. And once you have this ladder, it means that if you have an unknown sample, you can put that contrast that you measure somewhere on it, and therefore actually measure the mass. And so this is now commercialized by this company out of Oxford, and I've been to many places where they actually have these devices in the labs. We are now, and many other people are trying to see how you can actually use this information to go beyond proof of principle and do some relevant kind of biomedical studies. One of the things that we did, this was published also in 2018, is to uh, go and see what is being secreted from cells. So your cells are constantly interacting with their environments, and one of the things they do is they eject chemicals and take up chemicals. And these chemicals, again, could be proteins, or it could also, I'll show you, be larger particles. So in this case, this cell was chosen because we knew that it was going to secrete a protein called IgG. This is your that you know. And so we turned the laser field at a few microns next to the cell, so the cell doesn't see any light. But as it ejects its proteins, we can watch and basically see the proteins parachute down. And this is now, we can do this in real time as it's happening. And once you look at all of these things over whatever time you have, you could be doing for minutes or tens of minutes, then you can make histograms. And this histogram is basically telling you what kind of stuff came out. In this case, you see that the IgG component corresponds to this part of the measurement, and then there are other things there that we couldn't identify at the time, but we see that they're coming out. So this type of thing is work in progress, where you try to make it more and more useful for the real kind of application that medical scientists might have or biologists might have. Now, aside from proteins, there are other things that are being secreted or interacting with cells, and these are actually larger particles, so in a way they're easier to work with. A virus is one of them. But a very exciting animal here is the so-called extracellular vesicle. This is kind of like a soap bubble, if you imagine that it's a nanoscopic soap bubble. So it's a monolayer of double layer of lipids again, but it could have proteins that are embedded in this shell, and it could also have other stuff in it. So from here to here, it might be somewhere of the order of 100 nanometers, plus minus 50, let's say. And these things could be secreted and could also be taken up by cells. And this is an electron microscope image of one of these things. And you can see that through the process of imaging it, it's been kind of badly treated. And it's not easy to quantify this and to know how much material is inside and what the proteins are, because electron microscopy is not that sensitive to deciphering all these individual elements. So there are also optical methods, and of course we're always interested in contributing from the optics side. There are other optical methods. One of them has been around and again can be purchased commercially. It's called nanoparticle tracking analysis, NTA. And in this mode, you do something very simple. You have your sample, and in your sample, your suspension, these nanoparticles, whether these are the extracellular vesicles, viruses, drug-loaded vesicles, whatever it is, they're kind of swimming around. And when you illuminate them by laser light, you get the dark field image of them. And now what you do is you chase each one of them and make trajectories. And the trajectory tells you how slowly or fast they're diffusing. So from that trajectory, you can extract the diffusion constant. And the diffusion constant is proportional, inversely proportional to the size of the particle. And so this method then gives you a distribution of the size of particles that you have based on doing trajectories of all these individual particles. So it's wonderful, it works, but it works with dark field microscopy. And I told you the problem with dark field microscopy that the signal is too sensitive to size. And you can imagine that, if you have a sample that you have where you have 10 nanometer particles and 100 nanometer particles, the difference between those two is a factor of 1 million. And it's very challenging to detect samples over a range of 1 million signal in one shot. So the dynamic range becomes an issue, and IceCat helps because its dynamic range that is necessary is much smaller. So we basically did the same thing doing our iSCAT, and because we're more sensitive in terms of detecting small particles, we can also be faster. We put all the advantages together. The bottom line is that we can do better. So this is an example. This is now we have a dummy sample that is a mixture of 15, 20, and 30 nanometer gold particles. These are really small gold nanoparticles that are mixed together in one suspension. And NTA can't resolve them, doesn't have enough sensitivity or resolution to resolve these. And this is the signal that you would get from dynamic light scattering. This is an intrinsically ensemble, very smart but old ensemble type of technique that's also commercially available. So you can see that INTA can actually identify these three populations quite nicely, especially when you project them on this scale. Now, what we're doing in INTA is we're extracting the size from the diffusion constant, but we're also extracting the size from the size of the signal, because the size of the signal is an independent measure. I told you that's proportional to the volume. So you take the third root of that, then you get this axis. So doing this has allowed us to really do much better in terms of analyzing suspensions of very small particles, and we're pursuing this with many groups and kinds of collaboration to try to see how we can learn something. That was my paper, and I want to close this part in the beginning by showing you that so far we've been looking at, in a way, isolated nanoparticles, whether it was a protein or a vesicle, but these were isolated nanoparticles. And we can show that we have very high sensitivity, but we've recently shown that you can actually use iSCAT also as a wonderful microscopy. That's even if you go to a place that is as complicated as a live cell. Now, the problem with the live cell is, and this is what scared us for a long time, and we didn't even try things like that, is that obviously your cell is full of proteins and all kinds of organelles. So they would scatter a lot. And so you would expect a very bad speckle kind of situation. In particular, because there's dynamics, this speckle is constantly moving around. So we thought this would be absolutely hopeless. But we tried it at some point. And this is now a movie that I'll show you. This is a label-free video of inside of the cell, and you can see all kinds of interesting things that are happening with nanostructures in the cell. And there's essentially no speckle. The reason for this is that we're doing this in a confocal mode, so we can get rid of quite a bit of the speckle by the confocality of the optics. You see that things are moving on trails, and these trails are, in this case, the darker ones that you see are the so-called endoplasmic reticula. These are soft tubules that have diameters of the order of 100 nanometers. And usually you look at these things using fluorescence microscopy. And you probably appreciate now you don't have to do that. Your life becomes simpler. In addition to that, playing this movie again, you see now that you don't just see one type of organelle, but you see everything. You see vesicles that are moving around. You see other particles. We, in fact, don't even know what everything all is as it's happening. But it gives you an opportunity to figure out correlations between what's happening on one side of the cell and what's happening on the other side. So anyhow, from an optic point of view, it's very interesting because we're now going back essentially to normal microscopy, which you know from several hundred years ago. There's no labeling, there's no fancy anything. Basically, you shine light and you look at it under a detector. Here's an example of doing something similar, but on a cell that has been infected with viruses and has generated new viruses, and these viruses are now being pushed out of the cell by a kind of bundle of actin filaments. So the black spots are viruses, and again, they're not labeled, so you can see these individual viruses. Oops. you can see these individual viruses being pushed and moved by the tails that are attached to them. So we're right now analyzing all these things to submit. All right, so and the very last thing from the biology thing is not imaging, but it's more nano manipulation in a way. We really think that, you know, as experimental physicists, we want to draw on everything that we can do in terms of measurements, making setups and analysis, whatever. So this is now a simple looking method to label a cell at a very particular place and at a particular time. We call it a microkiss because you go lightly wet your lips and touch the cell and you come back. And, by doing this, you can, for example, introduce reagents or individual nanoparticles were shown to a part of the cell, and then you can watch them diffuse and see what they're doing as they propagate in the cell. All right. So I would like to thank a large number of people who contributed to this line of research over more than 20 years. The people in the lower line are right now mostly are still in working in a group. Other ones have graduated and moved on. So now let me come to the quantum optical parts, and someone tells me how much time I have to select. Avoid going over time. I'll try to do a tour of this. We've talked about the basics now quite a bit, and in a way, at least, you know, the people I've talked to, they're very competent in the quantum optics part, so I don't have to go into too much of the detail of that. These experiments are done also on molecules, but now we go to very low temperatures to make sure that the cross section of a single molecule becomes large. Remember, I told you that room temperature, we have dephasing issues, and the cross section is lowered by 10 to the 5. And we showed many years ago that if you really do extinction on a single molecule, if you do it at low enough temperature, where you get very narrow transitions from a single molecule, you can get a direct extinction signal that is of the order of 10%. So and 10% is not 100%. I will say something about that in a bit, but it is a very sizable interaction. That means that if you send 10 photons, one of them will scatter from a single molecule. And we've done a number of studies that were based on this very fact, but I'm not going to talk about them today. So let me just remind you that when we have a molecule, we have an electronic ground state and an electronic excited state. But of course, you have vibrational levels associated with each one of them because this is a molecule. And the transitions from the excited state to these different vibration levels turn out to be not of high quality, if you want, in the sense that these modes are coupled to the matrix, and they are essentially a source of decouplings. The transition from this excited state to this ground state, the lowest one, is very good, and that's the thing that is going to give us a very narrow line. So you can detect this molecule in two ways. You can detect its fluorescence, which is what has been done forever in lots of different labs for the last 30 years. That's this signal. And this is the simultaneously measured extinction of them. If you don't look at this line, but if you look at the same wavelength as you illuminate, that is in extinction. So that's kind of the transition situation that we have. These are the molecules that we use. So there's a range of what we call guest molecules and a range of host molecules. We dope these guest molecules into other types of molecular crystals. And again, if you go to very low temperatures, the property of this class of material is that you get very narrow lines of the order of tens of megahertz, which is comparable to the line width that you have from a single alkaline in vacuum. So although your molecule is embedded in a solid, in an organic crystal, its coupling to the matrix has been basically eliminated. And you're looking at this transition of an individual molecule as if it were isolated. The other thing is that, as you have your molecules in a crystal, because the crystal is never 100% perfect, each molecule sitting at somewhere in the crystal experiences a slightly different local effect, which means that its transition frequency is slightly shifted. So if you scan your laser, if you fix a spot, illuminate a certain region, or scan your frequency across, you will talk to a whole bunch of molecules that happen to have slightly different frequencies. And this is an important kind of weapon in terms of getting the molecule signals, although you have an outside. So if you zoom into one of these, that's this very narrow line that it's telling you. Now, why don't we get that 100% signal? Well, again, because we have these vibrational levels, and we don't have a perfect two-level system, but we have losses via these vibrational levels. And the way you can characterize this is something like a branching ratio. That is, what's the probability of light going down this way, so as if it were a two-level system, to going like that. And that's, in these systems, actually quite good. But it's of the order of 30%. That kind of reduces the cross section by some. And the way to recover this now is to enhance this transition so that it becomes faster than what happens here. And this is what we do by putting a molecule in a cavity. So people from quantum optics are used to putting things in a cavity to enhance things. And this is basically what's happening here as well. Except that now we don't really need, because we already are quite well along with 10% extinction, we don't need a huge cavity effect to get to something like 100%. We just need to enhance this maybe by factor 10 or 20. So what you do when you put your molecule in a cavity is you bounce your light around, and every time it goes, it has that sigma over A effect. But because the photon goes by a very large number of times, like tens of thousands of times, you get an enhancement factor. And the enhancement factor can be written as an S divided by the mode area, or it's the same thing as quality factor divided by mode volume, or cooperativity for those who are more familiar with it. So either way, what you want to do, you can imagine now, is that you want to put your molecule in a cavity and you want the Q to be as large as possible and V to be as small as possible. And we chose, for different reasons, to particularly focus on cavities that have a small mode volume. And the way we do that is by having a flat mirror. We put a very thin crystal. This is kind of crystal that you want to grow. You take one of the nicer ones and put it on a flat reflecting mirror. And on the other side, we now want to come with a very strongly curved mirror, so that we can bring it very close and make a mode volume that is as small as possible. Something up to around 1.2, right? So we make these by doing focused ion beam milling at the end of something like an optical fiber or an invented or any other structure that you might have. There are lots of little interesting technical details of how to do the experiment better, but conceptually, this is basically what you do. And then you can send your mirrors to be coated so that you have a bright kind of reflector there. You get a very high reflectivity, 99.995 type of thing with them. And then the advantage now is that you have this curved mirror, and the radius of curvature is of the order of, let's say, 5 to 10 microns. And you have the advantage now that you can tune the cavity frequency by changing the distance, but you can also move it laterally and focus on different molecules in your sample. This is the kind of thing that we record. This is now the spectrum of the so-called empty cavity, where the resonance is far from any molecule that is in it. And this is what happens if the resonance coincides with the resonance of one single molecule. And what you see is that there is a strong drop in transmission. And if you want, that's the extinction of the single molecule. But because it's an interference effect, you can see that it is also in reflection. Now, the opposite thing is happening. We then also showed that you can replace the laser by a single photon source. And the way you do that is you take a single molecule and generate single photons from it, and then take these single photons to the other single molecule that is embedded in the microcavity. For that, we need to couple two of our experiments. In one experiment, you have a cryostat to do the same thing that we've been doing, but you now focus on exciting the system in a way that you extract these photons from it. You put those photons through an optical fiber, take it to the cavity experiment, and there you eliminate the whole laser system and send these single photons onto the cavity and do the same experiment. Not going through the details, just to show that, we are now at a point where doing single photon and single particle experiments with a pretty good efficiency. They're doable in the lab, and you can think now of doing interesting things with them. But this type of system is still quite bulky and somewhat inconvenient, because I'm coupling two cryostats from two different labs. So to move on, to go to a kind of a more network type of place, which is what everyone wants to do these days, or everyone should be doing these days, is to scale up. And you want to look at a more complex kind of system where you have many nodes of individual quantum emitters that are coupled to each other via photonic channels. And this could be single photons, this could be many photons. So you could have coupled nonlinear effects, you could have coupled linear effects, but it gives you a completely new paradigm of light matter interaction, because your light and matter are now hybridized in an interesting way. The simplest way of hybridization, of course, is when you look at the strong coupling, where your coupling of a single molecule to the mode is strong enough so that you can treat this as a kind of a coupled pendulum. So your photon comes and bounces from the molecule, goes to the cavity, comes back, bounces from the molecule again, goes to the cavity. So it keeps doing this back and forth. That's the so-called regime of strong coupling, where you see this kind of dip that I showed you widening up into two separate peaks. So we showed that we're almost there. I'm going to skip over this. This is an interesting kind of single photon nonlinearity thing, but I want to focus on what's exciting right now. Is again finding ways to couple many molecules to each other via a common photonic mode. And so to make this manageable, we thought that we reduce everything or the size onto a chip, so that we make a chip-based resonator, and that's something like a microdisk. And then you can have essentially a photonic circuit. You can have waveguides to couple into and out of this microdisk resonator. And so these would be the resonances of this microdisk. And now you see these little dots, red dots on top. These are indicating molecules that we put on top. So we prepare our organic crystal on top of this disk so that there are molecules that happen to be close to the edge of this disk, and they can couple via evanescent modes to the resonator. And what you now see is a zoom onto one of the resonator modes. That's this broad one. And then this dip here is again the signal, the extinction from a single molecule that's coupled to that mode of the resonator. We also have electric, we have electrodes, and that allows us to apply electric fields and shift the resonances of individual molecules by a stark effect. And that allows us to tune these molecules to the same frequency, for example. So, because remember that if you don't do anything, different molecules have different resonances in the crystal. And if you want them to couple very well, you want to bring them to the same frequency. So there we take advantage of star tuning. And so here's an example. You have many molecules coupled to the same mode, and by tuning the voltage on one of these electrodes, you can this one remains more or less at the same frequency. This one scans through. And so again, I'm not going to go through the details of that. This paper actually has appeared a couple of months ago. This seems to be an older slide that's looked through. And basically reports on these experiments that we've done where we show that in a controlled way we can couple two molecules to the same mode of the microcavity. Now, what we're doing now, and this is unpublished work, and I'm not going to show you results, I'm just going to tell you kind of what we're doing, is to do something as in this previous experiment, but not in an integrated circuit. It turns out that from a material science point of view, it's quite challenging to continue along that road. I mean, one should push, but we have realized that in our other experiment, we can actually get results more quickly. So in this case, we go back to our open microcavity, and remember that we had a thin crystal, and there we have a whole bunch of molecules. And now we want to, what we're able to do is to really make two molecules or more talk to the same mode of the cavity. And there, your parameter space becomes very large. You can do all kinds of crazy things. You can change the detuning of the two molecules with the cavity and the molecules. And this is opening a very exciting regime where each of these molecules is now coupled to a mode of the cavity, and therefore it's interacting very strongly with that photon or with that mode. But now there are several that are doing, and through their interactions with a common mode, they end up coupling to each other. So this is the kind of thing that we're studying. I just flashed through works. One is this work that we published a couple of years ago. For those who are interested in experimentally in doing kind of near field optics, but don't like to have tips that break all the time, here's a tipless kind of approach, which we're excited about because it allows you to have a very robust kind of a setup for bringing, for example, an optical antenna to individual quantum dots or other emitters. And here's something that was just published where we take advantage of, this is now a little bit of a quantum optics type of idea brought into more biophysical studies. Biophysics people quite often look at single molecule fluorescence, but they would like to do that in a solution, in an aqueous type of environment. And we show here that by having a certain arrangement that we call an optofluidic antenna, we can change the emission pattern, which is usually just 4 pi, to something that looks like this, so that basically all the light goes towards the detector and doesn't get wasted. And there are some other interesting effects that come from a very confined fluidic system where the diffusion is manipulated, and all of these things kind of conspire to give us a lot more signal that you usually would have. And with that, I'd like to acknowledge people who are working in the quantum optics track in the group right now. And thank you very much for listening. Those who might be interested in postdoc opportunity, feel free to get in touch with us in any of these areas. Thank you.
Thank you very much, Vahid, for this wonderful talk. Now, time for questions in the audience.
Thank you for the talk. We're inspiring. I have a question regarding the first part of the talk. When we were doing this experiment to actually measure the weight of these molecules. We were comparing molecules which were have different weights, but also very different conformations.
Right.
So I guess you're limited by the diffraction. But is there any way that you can actually get some info of the shape of those molecules?
Yeah. So that's an interesting question, and the question actually comes up very often, but I never have time to include that in the main part of the talk. So you have if so. So you can imagine that from polarization information, you can get some shape information. But you can also kind of remember that your polarizability actually has a form factor in it. So the polarizability expression that I showed is for a spherical particle. But if you were to elongate it, then, for example, for an elliptical particle, there is a closed form that tells you about the eccentricity, how that comes into the denominator. And for other objects, there might not be a closed form, but you can simulate it and you can figure out how the polarizability depends on the shape and size. And so in principle, by having all that information and doing some kind of tomography, looking at different polarizations, you can extract that. But you would need more signal to noise ratio margin to be able to decipher these things. But people are working on that, and maybe we will too. It's kind of the next level of perfect. Okay, thank you.
Carlos, thank you very much for the talk. I have a question regarding the last part.
Right.
Talking particularly many molecules. So you mentioned that on the previous attempt with this chip, you were seeking the question of frequency of individual molecules with individual electrons.
Right.
So what in this more advanced setup in which you are able to use the optical, what are your prospects for getting many molecules in the system? I understand you need 1 electrode per each molecule, right?
Right. So we are actually doing that as well. You can in a very simple way have many electrodes that you bring close to a region. So we're playing with that to see how far you can go. So building electrodes into, for example, the bottom sample is one way of doing it. In this work that we're about to submit, we have done a little bit of a brute force by basically illuminating the system. If you illuminate a molecule, sometimes they move their center of frequency, and we've managed to put things on top of each other. Nothing is permanent in this type of work, but long enough for hours or days until you mess with it again. So long, definitely long enough for you to be able to do 6 rounds. But eventually, this is where you want to go. You want to put electrodes, and there are also regimes where you don't really want to couple all of them to the same frequency. In fact, what becomes particularly interesting is if you respect the inhomogeneity and find ways to couple them nevertheless. In a little bit along the line of what we were discussing before, that although you have detunings, you can couple all of them in different ways in a dispersive regime or a relevant regime too.
Are these two architectures exclusive, or could you have your own chip microchips and then make this open party on top and combine the two things?
No, you can definitely do that. Yeah. Just need to have motivated students.
So first, I think for the talk very interesting. I have a question regarding the first part. Again, it's also related to the first question. I wondered if there was any because you showed you mentioned there was a relation correlation with the volumes and the intensity of the scattering lights you have, right? And is there any difference within the intensity of regarding the globularity of the biomolecule? Like if it's more stretched or if it's more globular, is there any difference in intensity, for instance?
Again, yeah, so your question is really related to the previous question. So if you take a particular shape, depending on what kind of polarization you have, you might be coupling to it more strongly or less strongly, and that changes the intensity in a way. You have to keep in mind, though, that first of all, we usually do these experiments with circularly polarized light to make us less sensitive to these things. So in a way, on purpose, you do some things worse and some things better so that you don't have big variations in one sample. But also, depending on the way you're doing the experiment, if your molecule happens to tumble during the measurement, it averages over that anyway. So there are some cases where, in practice, that just doesn't matter. And there are some cases where you can try to extract that kind of deviation from spherical shape from your measurements. So in principle, the information is there in the optics, but in a similar and to some extent, what we're doing now when you do a scattering experiment, you're kind of conceptually combining imaging and diffraction experiments, right? A typical kind of neutron or X-ray diffraction experiment is also a light experiment, right? Which will be X-ray one. And then you look at diffraction. And now we're collecting everything and imaging it, but the information about where the light goes, depending on the shape of the object and all that, is somewhere all stored in the system. And you have to find ways to get at it. Again, it depends on your signal to noise margin, how well you can do this.
Yeah. Yes.
Hi, thank you very much for the talk. I was just thinking because you said like polarization matters when you do these experiments. I was thinking that you have like your incident field, and you have like this scatter field that I think should be randomly polarized once you get out of there. I don't really see why these polarizations matters in this experiment, right?
Why should it be randomly or polarized?
I just thought that if you have like let's say a gold nanoparticle, then the scatter field coming from that would not have the polarization from that is not dependent on the.
Oh no, it is. Yeah, so I mean that's also a kind of a well-defined situation, and so if you have your again, you can imagine that you have your spherical particle, and if you come with this light, you're going to polarize it in this direction, and then after that you have a dipole that is in this orientation, and that dipole is going to radiate in a particular way. It's not going to be randomly oriented. So the scattering from a nano object is well defined depending on its shape and the incident polarization.
In the previous question, you said that we use circularly polarized light, and so that we can nullify the effect of the shape. So how does circularly polarized light help?
We take generally circularly polarized light, so we're not very sensitive to. So if you were to use linearly polarized light, and your object happened to be linear, for example, a rod, and it's sitting like this, then depending on this angle, your scattering intensity would change. And if you use circularly polarized light, whether it's like this or like this or like this, it's almost the same.
Thank you.
I think this is a really question like following this discussion. Like, what are the selection rules in the objects? Like, for example, you take a linearly polarized light or circular, like all these enters in this cross section. How you know, like maybe some molecule is darker to some polarization, or does it depend on the orientation of the shape? Or
Right. So in case of molecules, they have a pretty well-defined dipole moment orientation. That is given by the skeleton of the molecule. For each molecule is a little different, but for each molecule it's kind of well-defined. So you know the axis along which the dipole is fixed. So in that way, I wouldn't say much about selection rules because it's a dipole transition and you have normal dipole transition selection rules. But if you were to rotate your the polarization of your incident field, you clearly say get a sinusoidal shape when you're parallel to the dipole moment of your particular field. And that's actually an interesting point because when these molecules get embedded in a crystal, then you'll find essentially all of them aligned parallel to each other because they adapt themselves to the crystal environment. And the way the molecule sits like this, the ones that is dipole, for example, is also like that. It's always like this for all the molecules in the crystal.
Question, because I know there's a little bit of some of the issues here, and I wonder what are the prospects now of putting these molecules on this configuration, for example, where you could at will place your molecules at different positions, and I know there were some progress on this, and I wanted to know what is the status now and what is the prospects of.
Yeah, so there's a paper in art paper we show that we print nanocrystals and this I didn't say anything about this, but they've been working on a method where you print small nanocrystals in a particular method. And by doing that, you can go print it anywhere you want. You don't have 100% control, but you're a lot more control than in a bulk type of thing. And so there are opportunities, but again, there are experimental challenges that don't prevent you, but slow you down in all products. So even you have a nanocrystal, then these crystals are quite often volatile. So you have to work harder to make sure that they don't evaporate as you print them and you transfer them. These are all kind of mundane issues, but they slow down our progress because every time you have to deal with another thing. So things like that, as you know, they're all over the place. I painted a very rosy picture of the world. But yeah, so in principle, you can go and do this. And one of the options here, connected to the previous question you asked, is to print a crystal and where their electrodes are pointing, so that you have good control over those molecules. They can't think of it.
Thank you. Session, and thanks, Vahid.
Thank you very much for this.